what I'm going to talk about now in this video is going to be how to calculate and draw the first 5 energy levels of an electron in a 2D particle in a box model with Lx and Ly equal to 2.50 nanometers, right? So it's going to be a perfect square in these cases. So the first things first, right, we want to write out what our equations are. And so the equation for a 2D particle in a box, right, you're going to have an x dimension and a y dimension, and they're going to be basically just simply taking what we have as the 1D particle in a box is, right, and you're just going to multiply them with each other in those scenarios, right? So if you remember what the equation is for a 1D particle in a box, you can just simply assign one of them as x, one of them as y, multiply it together, and you're going to get what we're going to have right here, right? So in that case, right, we have the wave function. It's going to be, based off of the different energy levels. And one important thing to think about for a 2D particle in a box is that you can have different n levels for the different parts of it, right? So the y dimension can have a different n level than the x dimension does, and that actually generates different energy levels. They also have then different shapes and different ways that they look in those cases. And so, but going back to the wave function, right? The wave function, if you multiply the two of them together, is now going to be 2 over the square root of Lx times Ly times the sine of nx, right? And so n is the quantum number, the energy level of the x dimension, times pi times x, right? So the position of that wave function in the x dimension over Lx, right? Which is simply the distance, or sorry, the length of the x component of it, times the sine of ny, right? So now that's going to be the quantum number, or the energy level of the y dimension, times pi times y, right? So that's the position on the y dimension over Ly, right? And so that is the wave function for a 2D particle in a box. And so similarly, right, for the energies of the different possible energy levels, right, because you're going to have different combinations of them, what that equation is going to be Planck's constant squared, right? So h squared over 8m times nx squared over Lx squared plus ny squared over Ly squared, right? So, you have to segment out the quantum numbers with the different lengths, right? Because those are going to impact what the energies are. Now, a nice thing is, because in this case right here, right, both Lx and Ly are equal to each other, we can actually pull those out and simplify our equation, right? So it just simply becomes h squared over 8ml squared, right? So times nx squared plus ny squared, right? So that's looks extremely similar to what we had done in a 1D particle in a box video, right? Where we were able to have this whole thing right here pulled out, right? Where we have essentially all constants based off of the system that we're looking at. And the only thing that we really have to then change is what the different n values are for the x and the y directions. So that makes our lives a lot easier, right? Because if we're going to calculate all these energy levels, we just calculate that part first, and then all we have to do is just simply slot in the nx and the ny components in those cases. And so one important thing, right, to do is write out what our constants are as well. So in this case, right, we're doing an electron, so the m is actually going to be the mass of an electron. So the mass of an electron is 9.1094 times 10 to the negative 31 kilograms, right? And so an important thing, again, is that the units have to be in kilograms, because otherwise it's not going to cancel out with Planck's constant, right? Planck's constant is in kilograms. And Planck's constant, right, is h is equal to 6.626 times 10 to the negative 34 joules per second. Or if you wanted to do it in a different way, right, in terms of units, right, it's going to be kilograms meters squared over seconds, right? So that's another way that you can write it out. So that way units can start canceling out the way that you want them to. Cool. So to make our lives easier, right, we can now calculate out what essentially that constant part is in those cases, right? So if we're looking at this whole system, right, E is equal to h squared over 8ml squared times nx squared plus ny squared, right? And so if we do that and we plug in the different constants that we have, right, what we have is 6.626 times 10 to the negative 34. And I'm just going to write it out as the kilograms meters squared over seconds, right? And so that gets squared over 8 times 9.1094 times 10 to the negative 31 kilograms times, and now an important thing to think about is that the box length has to be converted into meters. And so to do that, right, from nanometers to meters, all you have to do is just simply multiply by 10 to the negative 9. And so in this case, right, it's just simply 2.50 times 10 to the negative 9 meters, right? And so that right there is our unit. And so all of this then, I'm just going to, now that we have all these things, I'm just going to move this to give myself some space. Right, we have all this, and so that's just simply going to be multiplied by nx squared plus ny squared. And so if you multiply all of that out, what you get is that that's going to have a value of 9.640 times 10 to the negative 21 joules, right? And then that's just simply going to multiply by nx squared plus ny squared. And so now we can just simply calculate out what all the different energy levels are. So if we look at it, right, we have the first energy level, right, that's going to be the 1,1 energy level where n is equal to 1, nx is equal to 1, and y is equal to 1, right? That's going to be our ground state in this case. And so what that's going to be is 9.640 times 10 to the negative 21 joules. And that's now going to be times 1 squared plus 1 squared, right? So that's going to be 2. So 2 times, you know, our value that we have right here. And so that comes out to being 1.928 times 10 to the negative 20, right? So that's the energy of the first energy level. And we can tell, right, that that's a different value than what we were getting for the 1D particle in a box, right? If you look at that video, or if you calculate that out for a similar box length, and it's going to be, right, double that. So that's really cool. So the next energy level, right, is going to be then a combination actually of two different ones, right? So you can either have the 2-1 combination, right, where nx is equal to 2 or nx and ny is equal to 1, or you can have the situation where nx is equal to 1 and ny is equal to 2, right? And so both of those technically are different states, but they're actually going to be at the same energy, right? So they're going to be degenerate in these cases because there's no difference between, you know, which combination you have between the two of them. They're technically different states. They look different, you know, in spatial visualization, but in terms of what their energies are, right, they're going to be exactly the same. And so if we do that, right, it's just simply going to be the same thing, right? 9.640 times 10 to the negative 21, and that gets multiplied now by 2 squared plus 1 squared. And so that comes out to being, right, 2 squared is 4, 1 squared is 1, so we're multiplying everything by 5, and so what we get now is 4.820 times 10 to the negative 20 joules, right? So that's the energy level of the 2-1 and both the 1-2 energy levels, right? So both of those have that same value, right? And the way that we can visualize, right, so I'm just going to kind of jump ahead a little bit and draw out what everything looks like. It's really hard to draw these 2D images in a way, right? These 2D wave functions. And so the way that I'm going to do it is going to be like a bit as a topographical map. So, you know, for the 1-1, so if I draw that right here, right, I'm just going to simply draw my square, which is my 2D particle in a box, right? The way that that's going to look, I'm just going to use some different colors, right, is that essentially, right, you're going to have a whole bunch of circles going upwards, right? So if you've ever seen a topographical map of like a mountain, right, the more, like, every circle is essentially like one higher elevation, so to say. And so you're going up, 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 and kind of making this hill in this case, right? So this is the, so this right here is the nx equals 1 and y equals 1 energy level. Now for the other ones that we just did, right? So if we have then the nx equals 2 and y equals 1 energy level, one important thing to think about, right, is that we know from the 1D particle in a box that if you have an n value equals to 2, right, you're going to have one node, right, and it's going to be at the halfway point. And so we can, you know, when we're drawing these, we can make our lives a lot easier by drawing it in initially, right? So we can just draw in our node by just having it be this, you know, little line that goes right here, right? So that's you know, essentially cutting my x direction in half. And so if we're drawing then our topographical map, right, what we're going to have is that if you're looking at it from the y direction, right, it looks like you're essentially, you have right ahead of you, you know, from the y direction, right, it's just simply going to be a single hump, right, because ny is equal to 1. But if you're looking at it from the X direction, right, you're going to then have, the two parts to it, right? It's going to have like the top and the bottom in those cases, right? And so then when you're, actually able to rotate it, it looks like you have like two different, like you have a hill and a valley in those cases along those things. And so the way that we can then draw that, right, again, topographical map style, right, is that on one side, it's going to be going up, right? And that's what we would expect in those cases. And then on the other side, I'm going to use... let's use black, right? And then the other side, right, you're going to have it go downwards, right? And so you're going to have essentially a hill, right, and then a valley in those cases. And then, if we're looking at the other system, in this case, right, so now if we have the nx equals 1 and y equals 2 system, right, it's just basically as if it was rotated by 90 degrees. So right now that nodal plane is along the y direction, right, where we're cutting that now in half. And so what we have is then down here, right, is going to be this part. And then up here, right, is going to be then the part that goes downwards. And so, right, so they look pretty similar, right? They're just simply rotated, but technically in space, right, they're occupying different areas. And so they're two completely different states, but they are at the same exact energy, right? So they're degenerate in these cases. So that's how you draw, right, those two. Now the X energy level that we would look at, right, is going to be the 2, 2, right? So nx is equal to 2 and y is equal to 2. So again, we can just plug in the number that we have here. So now it's just simply 2 squared plus 2 squared. Right, so that whole value is going to be 8, and so we multiply that by that value that we had gotten, so that's going to be 7.712 times 10 to the negative 20 joules, right? And so if we were to draw what this one looks like, right, the 2 energy level, right, so for this, so nx equals 2 and y equals 2, what we can identify, right, is that we're going to have one nodal plane in the x direction, but we're also going to have one nodal plane in the y direction. And so what that gives us is that we're going to have two hills, right? One's going to be here, right, because that's going to be our starting point essentially for everything. And then we're also going to have another one here, right, because the nodes have to transition everything that we have in these cases, right? So we have then the nodes, right? So we have essentially two hills and then two valleys in those cases, right? And so this is what the 2, 2 looks like in this case. Next, right, we would have go up to then the 3, 2 energy level. Or actually, the next energy, wouldn't be the 3, 2, right? Because the next combination we can have is going to be the 3, 1 slash the 1, 3. Right, so we can have any nx is equal to 3 and ny is equal to 1, or we can have the nx is equal to 1 and the ny is equal to 3, right? Because that will be the next energy level in this case. And we'll see it in a second, right? Because I'll also calculate out the 3, 2 and the 2, 3. But we have this right here, right? And so again, we're just going to use that constant that we'd already calculated out. And so now it's going to be 3 squared plus 1 squared. So that comes out to being 10, right? Because we have 3 squared is 9, 1 squared is 1. Add those two together, we get 10. And so now what we have is that the value is going to be 9.640 times 10 to the negative 20 joules, right? So that's what that energy is going to be. And if I go ahead and I can calculate the 3, 2 right now, right, slash the 2, 3, right? Again, those are going to be degenerate as well. And so now that's going to be 3 squared plus 2 squared. So that comes out where the n values, right, is going to be 9 plus 4. So that comes out to being 13. Right, and 13 is higher than 10, right? So we would expect then in the energy level to be higher for the 3, 2 than it would be for the 3, 1, and also for the 2, 2. And so what we get is a value of 1.253 times 10 to the negative 19 joules. Right, those are what those energies are, right? And so then if we want to look at what those look like, right, if we were to draw those out, again, you just simply treat it as if it was two different 1D parts where you're trying to draw in your nodes. And so if we have the nx is equal to 3 and y is equal to 1 energy level, right? You're going to have then along x, you're going to have 3 nodes. So you're going to have 1 and then 2 here. And then along the y direction, right, because ny is equal to 1, you're not going to have any nodes. And so we can just simply draw this now. So we have one thing here, right? And then another one's going to go upwards right here. And then, is it black? And then this is just simply going to, right, look like that right there. So you have, you know, essentially a valley side by side by 2 hills in that case. And so we can then do the same thing for the 1, 3. So if we have now the nx equals 1 and y equals 3 scenario, what we can see is that now we're going to have the 3 nodes along the y direction. And so we can just draw out, right, that we're going to have a hill here, right, and we're going to end up with a hill as well. And then we're going to have this valley right here. Right, and then so in the case of the 3, 2, right, so the 3, I'm going to actually, let me draw the 3, 2 on the next page, just because that way I'm not cramping things, right? So the 3, 2, right, so if we draw this out, nx equals 3 and y equals 2, right, what we're going to have is along the x direction, right, we're going to have 3 nodes, so I can draw those in. And then along the y direction, right, we're going to have 2 nodes. And so now, right, we can draw in our hills and valleys, right? So we're going to have a hill here, right, because this is going to be our starting point. So there's going to be a hill here, right? We're going to have a hill here, right? And then we're also going to have a hill here in this case, right? Because we're going to have to switch at every node to valleys, right? So we're going to have a valley right here. We're going to have a valley right here. And then we're going to have a valley right here. All right, and that's what the N32 looks like. And then we can draw the ny equals 2, or sorry, not ny, nx equals 2, and y equals 3, 1. And so again, same thing. First things first, right, we're going to want to draw in our nodes. And so along the x-axis, right, there's just going to be 1 node because nx is equal to 2. And then along the y-axis, right, there's going to be 2 nodes because ny is equal to 3. So now we can start off again, right? So we're going to have a hill here, right? We're going to have a hill here. And then we're going to have a hill here. And then we're going to end up with valleys right here, right? And that is how you draw the different energy levels for a 2D particle in a box, and also how you calculate the energies for those different energy levels.